Introduction to Light Part 2, Properties of Light. We're going to start exploring a little bit more what it is about light that's so important, what gives these different types of light their properties. Light travels as a wave. In the previous diagrams, we had seen that little sine wave used multiple times, and that's because that's the way that light travels. It travels as a wave. We talked about something called wavelength. On this diagram, we see wavelength here depicted as the distance between these two peaks on the red graph. The wavelength is the distance between any two equivalent points on the wave. So for instance, these two peaks or these two troughs, as they would be called. You could also do the distance between any two equivalent points anywhere else on that wave. For instance, here and here. That would be the same wavelength. Now, light travels as a wave, but the reality is that light actually travels as something called two waves, the electromagnetic wave. It has both an electric field direction and a magnetic field direction, and those directions are perpendicular to each other. Now, if you've never taken physics, this all sounds just ridiculous, and if you have taken physics, you may remember a bit of this. But this is the reality of all forms of light. They do travel as an electromagnetic wave, and that's why we call it the electromagnetic spectrum. Now, this wavelength. We've talked about the fact that light, and in its different forms, really just varies in wavelength. A really good example of this is to simply look at the visible light, the colors we already know. If we look at violet light all the way at the top of this diagram, we see that the peaks are very close together, about 400 nanometers in distance. That's a very, very short distance. When we look at the red all the way at the bottom, we see that the peaks are a little bit farther apart, about 665 nanometers. And all the colors of light in between have varying wavelengths. This is ultimately the difference between the different types of light. When you go from radio waves, which have a really, really long wavelength, much longer than that of the red light we see here, all the way up to gamma rays, which have a very, very short wavelength, much, much shorter than the violet light we see on this diagram, we get different properties. And those properties come back to this little equation right here and one other that we'll learn about later on. This equation that relates wavelength to frequency, utilizing the speed of light, this is really the big one. Now, that frequency and the wavelength relationship becomes really important when we start talking about the energy of the light. And that energy is ultimately what we tend to reference as being good or bad when we talk about light. The reality is quite different from that, though. Looking at the relationship of frequency and wavelength, we see that in this center diagram here, that a shorter wavelength has a higher frequency. A longer wavelength has a lower frequency. Now, frequency is defined as the number of waves that pass through a given point in a second. So oftentimes when we're talking about frequency, it's got a unit of per second, or second to the -1, also known as hertz. And this is something that a lot of people are aware of, but they probably never thought much about it. When you're tuning into a radio station in your car, that's measured in megahertz. So we use this hertz unit to represent a frequency, or just per second. Now, an example of how a longer wavelength can equal a lower frequency, I'm going to compare here two people. This person on the left is walking on stilts. His legs are pretty darn long. This guy on the right is Usain Bolt, the fastest man on the planet. Now, the guy on the left, his legs are really, really long, and you can imagine his steps are going to be quite a bit slower. So the odds are good that even though his stride is pretty long, because he's taking less steps, he's probably going to not travel so quickly. Usain Bolt, on the other hand, his legs are considerably shorter than the guy on stilts. Therefore, his legs can move a lot faster, and he'll travel a much longer distance in the same amount of time. And this relationship actually holds true to light to some extent. Light travels the same distance no matter what, but it does it with different energy. Now, before getting into the energy of it, let's look at the different types of light and let's talk about their properties. Let's start on the left side of this diagram with the radio waves. Now, radio waves are what we use for tuning into the radio on our car, how our cell phones can communicate with satellites. We use radio waves for different types of imaging, medical imaging, all kinds of stuff. Now, radio waves have a very, very long wavelength, about the size of a football field or longer. They're measured in kilometers. That being said, their frequency is very, very low, so they don't have a very high frequency. After radio waves, we've got microwaves. Now, microwaves are the same type of light that we use in our microwave ovens at home. Microwaves have a shorter wavelength, a little bit higher frequency. That frequency just happens to coincide with the frequency, the vibrational frequency of water molecules. If we look at a water molecule, it has two bonds between oxygen and hydrogen. Those bonds vibrate. And if we can increase the rate at which they vibrate, we'll increase the energy of the water molecule and therefore increase the temperature of the water. Microwave ovens work by emitting microwaves at a very specific frequency that will cause the bonds in a water molecule to vibrate and therefore heat up our food. This is why when you have food that is dry, it doesn't heat up very well in the microwave. Next, the most important one, this little section here, we've got infrared, visible light, and ultraviolet light. Now, infrared light is something that we all know very well, even though we may not know that we know it. Infrared light is also known as heat. Anything that emits heat is actually just emitting infrared light. Now, infrared light has an even shorter wavelength still compared to microwaves and radio waves. It's got a higher frequency. Now, infrared light, we know it is heat, and the best source of it that we know is the sun. So what that tells us is that in reality, the sun is actually just shooting a lot of light at us. And that's true. The sun is emitting quite a bit of infrared radiation right towards the Earth. About 50 to 60% of the light energy coming from the sun is in the form of infrared radiation. Now, next up, this tiny little sliver of light in the center is visible light. And this should put into perspective how much of the light range we actually see. Visible light is the only kind of light that we can see with our eyes, and it makes up just this tiny little fraction of the electromagnetic spectrum. After visible light is ultraviolet. Now, everybody knows ultraviolet, especially here in California, where the UV index can be pretty extreme. Ultraviolet is what most people know as the type of light that comes to the Earth from the sun that can do damage to our skin. Some people like to think of it in a bit more positive way. It's the type of light that comes to Earth from the sun and can cause us to get a tan. Now, ultraviolet light is an even shorter wavelength still, an even higher frequency than what we had seen before. After ultraviolet are X-rays and gamma rays, and these most people know can be very harmful. These are just types of light. They have really short wavelengths and really, really high frequencies. Now, one thing to think about is the fact that we can have all these different types of light, and we know that X-rays and gamma rays are bad for us. We know that ultraviolet light can be bad for us. We know that infrared is really just heat. Microwaves can warm up water. Radio waves seem to be pretty harmless. How is it that visible light can exist right in the center of that spectrum and be completely harmless to us? And the truth of that is that visible light actually can be harmful. If you look at where it is, in between infrared and ultraviolet, you would think that there would be some amount of energy associated with it, since infrared and ultraviolet are pretty powerful in and of themselves. Visible light, we just get it in very, very low intensity. If we were to increase the intensity of visible light, perhaps with a laser we could actually cause visible light to have enough energy to actually harm us.